Hey everyone, welcome back to MLWorks. In this video, we'll be discussing about post-training quantization. In the previous video, we discussed about quantization where we learned how to reduce the model size and how to speed up the inference. We also learned about different types of quantization like floating type quantization or integer type quantization. So as part of this video, we'll be applying post-training quantization, meaning you will have a trained model and you will be applying quantization on top of it, and we'll be using PyTorch for this particular exercise. So basically for post-training quantization, as I said, you will need a fully trained model and which leads to a simple and quick implementation. But since it is already trained model is present, what you will end up doing is during the quantization phase, you will be moving from higher precision to lower precision for the parameter values. So this will directly affect your performance when it comes to when you're testing it out on the evaluation data set. The advantages is it is easy to integrate since you have already a trained model is present. You just have to apply quantization and you don't need to modify the training code as well, and which will directly reduce the model size and the inference cost. The limitation is, as I said, the accuracy is dropped because some models are highly sensitive to the precision value of the parameters. So if you modify from floating point 32 to integer 8, there is a drastic change in terms of precision and which will directly affect your accuracy. So with that understanding, let's implement post-training quantization. So first we'll be loading the CUDA modules with the help of this command. So we'll be setting out CUDA home and point it to the CUDA libraries. So let me run this. Now, as part of package imports, we'll be importing all the modules related to torch and then some modules related to time and warnings. So what we do is we ignore certain warnings here and then we check whether we have CUDA or not. Then we set our device. CUDA is present, then it will be device will set as CUDA, otherwise it will be set as CPU. And then we create a parameter called skip CPU, which is set as true because we want to test our model on GPU instead of CPU, and it will make it much faster if you are testing it on GPU. While this is getting imported, let's talk about downloading and pre-processing the data. So for this exercise, we'll be downloading Cypher 10 dataset and apply certain transformation on top of it. The transformation include resizing the image from whatever size it is present into 32 cross 32, and then we convert it into PyTorch tensor, and then we normalize with the help of this value 0.5, which is mean and standard deviation. So we normalize, and these are the transformation we apply it on the data set. So if you see here in the training data set, we mention the data set we want to download, and download is set as true. If it is not present, it will download, otherwise it will check for the specific data set inside your directory. And while you're downloading, you also want to apply the transformation, which is this one. So we create data set and data train loader, and then test data set and test loader. And these are certain parameters including the path where you want to set whether it is training, you want to keep it as true. And then we have certain parameters related to batch size, if you want to shuffle the data set or not, what is the number of workers you want to use, and drop last is set as true. So these are different parameters, and for training and testing the data set, and then we create something called as calibration data set, which is a subset of your training data set, and it takes around 256 values from your training data set. Then we create a dataset loader, which is based on calibration. Here we have a calibration dataset, and we create a batch of 128. So basically this will be used when you're trying to quantize your model on a specific dataset. So we'll be using this specific data loader. So let me import this. Now let's talk about downloading the model. So we'll be downloading ResNet 18 and we'll modify certain configuration with respect to that model. So we modify the number of classes that we want to predict as number is 10, and we modify the convolution one as this specific module, and then we remove the max pooling with identity module, and we store the model or push the model to CUDA device. So if I go back here, you will see when we import the packages, we see the PyTorch version we are importing. The device that got used is CUDA, and we are skipping the CPU evaluation. So here we will be downloading the model, modifying the parameters or configurations of the model such that it can predict around 10 classes, and finally we are storing that model to device or moving that model to device. So now let's talk about train and evaluation function. So if you have trained the model, you know that you have to load the data set, and then you have to iterate through the data set through a number of epochs, and then you have to calculate the loss function, and then you have to update the weights. So that is the general flow. So here you have the specific set where we test whether the model is already present or not. A trained model is already present or not. If it is present, then it will go to the specific print statement and it will load the model. Otherwise, what we'll do is we go ahead and train a model. So this will be the first scenario if you don't have a model trained already. If you are training the model, then you should also have criterion and optimizer to calculate the loss and updating the weight. And this is the whole function or set of lines for running the model and updating the parameters, and finally saving the model once the model is trained. So our focus is more on quantization. So we are not interested in how to train a deep learning model. We are interested in how to quantize the model. So this is just a function for if the model is not present, then you can also train a model as shown here. Then once a model is trained, you will be evaluating the model, for which you have to run the model in Torch no grad, because we don't want to update weights during evaluation. By setting this, we avoid updating the weights, and then we run through the test loader, and then again get the predictions from the model and calculate the accuracy finally. So let me run this as well. Now let's talk about utility function. First, we'll be talking about how to switch between GPU and CPU. So since we are avoiding running the model in CPU, we won't be looking into that aspect. But for the sake of understanding, we are creating multiple utility functions. So first is timer, where we calculate the time taken for doing the evaluation. So we are setting that here in this class, timer class, where we have initialized self.CUDA, where you have starter and ender event, and you have start function and then stop function. And if you're testing on CUDA, then it will run this if statements, and it will start the recording or start calculating the time. And if you are using CPU, then it will go ahead and use these else statement to calculate the time. So next we write a utility function for estimating the latency. So we have some sample inputs, and we are running it again under no grad. So we don't want to update the weights of the model. So here we evaluate the models, and then we get the mean time taken for the evaluation and what is the standard deviation of the timings. And similarly here also we do the same, because we call, if you see here, right, we call this estimate latency here. This is the function of, this is the estimate latency. So if you are using CPU, it will do this. Otherwise, we'll use the model in CUDA and execute this function or this set of codes. And finally, the utility function for finding the size of the model, which is print size of the model, get the state dict, which is the saving the file or model file, and then getting the size of the specific file and putting it in terms of megabytes, and then removing that file. So these are the different utility function for finding the latency of the model, finding the size of the model. Next step is to, here what we do is we make a call to the train function. We check whether the model is present inside this path. If it is not present, then it will train the model. Otherwise, it will use the specific model, existing model. So yeah, the model is already trained, loading the model from this path. Now what we do is we just test it out on the evaluation aspect. So here if you see in the evaluation, what we do is we do around 50 iterations under for the same set of sample inputs, and then we see the time taken for the inference by seeing this timing we have, right? So using that we'll be calculating the time taken for evaluation. So for the original model which hasn't undergone quantization, what is the time taken, what is the size of the model, what is the accuracy? So we'll see that here. So this is the size of the model. This is 44.77 MB, and accuracy is 80.47% and latency is 18.84 plus or minus 1.33 millisecond. So this is the latency in GPU. Now what we want to do is we want to apply our post-training quantization. We have our model stored here, which is full model.pth. So let's talk about PTQ now. There are two key modules for our PTQ for quantization. One is prepare P2E, which is PyTorch to export, and convert PyTorch to export. So it contains two key functionality. First is observers, and there is fuse model. Fusing the eligible convolutional and batch norm layers. It will try to combine multiple operations as one, such that the amount of time taken for computing, right, it will be reduced. Then we also add observers like min-max observer. And if you remember from the previous video, I talked about how to calculate for integer quantization. You have something called a scale and 0 point, for which you need to calculate min-max of parameters, min-max of your quantization range. So those can be inserted or calculated with the help of observers inside your model. So as part of this step, what we do is we combine multiple layers as one, and we are also adding observers which will collect the min-max of your activations that is happening inside your model. So that is the preparation step, and then we have something called as conversion step, which will remove the observers because we have already calculated the min-max. So once you calculate the min-max, you will be able to move from floating point 32 to integer 8 by using that calculated statistics, activation statistics, and then you will remove those observers and apply those whatever statistics we got and quantize the model from FP32 to integer 8. So there is a lot to understand here. So you want to first prepare the model for quantization by inserting observers and fusing the layers. Once you have done that, then you have to remove the observers because it has already calculated the activation statistics. Since you have calculated it, you want to apply it, which is done in the conversion step. And then we use something called as x86 inductor quantizer, which is the module for applying quantization, and x86 represents the computer architecture. So it holds the quantization strategy and which layers to quantize and which data types to use. Now let's talk about implementation of quantization, where we import the two key modules, which is for preparing the model for quantization and then converting it to quantized model. And we use a quantizer called x86 inductor quantizer, which contains the quantizer strategy. So before we do that, any of the quantization, we have to understand or prepare the model which is already trained into a graph, such that you can modify that graph into a format from floating point 32 to integer 8. So for that, what we have to do is we take a sample input and store it into CUDA device, and it is a batch size of 128. So we take that sample input and use this module, which is torch.export for training, and this is only applicable for PyTorch 2.5 and above. And so you take in the model which is already trained and pass in the sample input, and under the hood PyTorch will create the computational graph which will be used for quantization. So this is the step for PyTorch 2.5 and above, and this is the step for creating that graph for PyTorch 2.4. So after doing that, we initialize our x86 inductor quantizer, and then we set the global configuration for that quantizer. And then we fuse the layers inside this export model and add certain observers to calculate the activation statistics. And once that is done, we prepare it for the quantization process. Now we take the prepared model and we calibrate it. So if you remember from the previous video where I talked about calibration, we do calibration when we want to convert from floating point to integer, and we calculate values like scale and 0 point. So for which you need to have min max of your tensor and min max of your quantization scale. So we'll be doing that, all those operations, that scale and the 0 point calculation, all will be happening here with the help of this specific calibration function. And we finally get a quantized model. So finally, when you call this convert P to E, so you will be converting your model to quantized model after applying the calibration. And at the end, for further optimization, what we do is we remove certain layers or modules which are not used, and further reduce the number of parameters that the model has to go through during inference. So this is the certain parameters that you have to use for that. So now here we finally test out our model and get the model size, what is the performance in evaluation side, and then we check the time taken for it. So the model size is reduced by 4x since we moved from FP32 to integer 8, which is 4x less. And the quantization accuracy, right, after the quantization it is 80.51. If I go back here, so it is better than the previous result, or it is almost similar to the previous result. But if you see the time taken, the latency, it is little high, because what happens, right, since we are performing this adding the observer and then removing them, so we are doing all those stuff, so it is taking some amount of time for that as well. Now let us further optimize this quantized model. What we do is we use something called as C++ wrapper. Now basically what happens, right, when you are using Torch inductor, by default it will use Python code for invoking the kernels and external kernels. Now by using C++ wrapper, we'll be further optimizing the inference cost. So let us see that. So first we import this config and from inductor, then we set the C++ wrapper as true, and again compile the model into C++ version. So this is the optimized model. Now let us run this again. So the model size remains quantized. So we can see the accuracy is reduced a bit, and if we go back here, it was 80.51 and here it is 79.29. So it has almost 1% it has reduced, and latency is also it is lesser than the general quantized model. It is lesser than that, but it is still in between the original and the quantized model. The key takeaway from this specific video is how to quantize, and it comes down to this specific block of code where we are preparing the model for quantization by fusing the layers and then finally adding the observers to it. And once the model is quantized, you want to ensure you don't have those observers as well. We have to remove them. So those are taken care while we are saving the model here. With that, I'll be concluding this video. Thank you for watching.